Hello. First of all, I would like to thank the organizers for the kind invitation to give a talk to this wonderful international audience. And if there was no COVID, this wouldn't be possible. I think this is a wonderful platform that you watch other people's talks, participate in their talks while you're sitting in your home office and having your coffee so that we don't need to fly anywhere. All right, I'm going to start off with the cutting edge applications of smart material systems. And if you're not familiar with smart material systems, this is for you. And then I'm going to share the outline of my talk next. All right, let's get started. All right, let's quickly talk about cutting edge applications of smart material systems. And the first example that I want to show you is the biodegradable piezoelectric pressure sensor developed by a research group at the University of Connecticut. And this could be used by doctors to monitor chronic lung disease, brain swelling, and other medical conditions before you dissolve this piezoelectric element safely in a patient's body. And the second example I want to share with you is the piezoelectric transistor developed by the Watson Research Center at IBM. And it works on a novel principle. Essentially, you apply the electrical input that is converted to an acoustic pulse by the piezoelectric element here. Right, here is another application of piezoelectric smart material system. So we have a shoe sole with an embedded energy harvester with the battery and electronics, all integrated in each sole. And when you walk, obviously, this harvester is going to harvest the energy and it's going to power up certain electronics needed. And this is developed by University of Wisconsin-Madison researchers. And in fact, this is a startup company. My next example is developing a smart trail by the Penn State researchers. And the whole idea is to harvest small amounts of energy to run mobile devices or sensors for health monitoring. And this is done by sandwiching lots of piezoelectric ceramics in between two elastic polymers. And the whole idea here is to add as many piezoelectric ceramics as possible because most of the energy is absorbed through the polymers. All right, here's the outline of my talk. So in the first part, I'm going to focus more on the modeling aspects of piezoelectric beam models. And these are novel beam models. Hopefully some of you would be interested in working on those models in the future. And in the second part, I'm going to talk about the controllability and stabilization recent results. And in the third part, I'm going to talk about more on the different scenarios where we have a delay in the feedback controller or memory in the material or thermal effects added to the game or fractional damping added. And in the fourth part, I'm going to work on nonlinear models when you assume large displacement assumptions. So we have nonlinearity added to the PDEs. I'm going to compare that to linear models. And I'm going to talk about some numerics that I have been recently working on. And hopefully, if the time is left at the end, I'm going to talk about the Wolfram demonstration projects that I have been working in the last 3 years with my undergraduate students. And two of our works are already published at the Wolfram site. All right, let's get started. Let's first talk about vibrations on non-smart, simply elastic beams. We have three major variables. So V denotes here the longitudinal displacement of the center line of the beam. It's essentially the stretching type motion. And W represent transverse displacement of the center line of the beam, which is essentially the bending motion. And psi is the rotation of the beam. And from this moment on, dots are going to represent time derivatives and primes are going to represent space derivatives. All right, let's start with the Rayleigh D Model, or so-called Kirchhoff B model. So we have one equation, one wave equation, in fact, describing the longitudinal type motion, and you have the beam equation here representing the bending motion. And these are completely decoupled because we're using the small displacement assumptions. In other words, we're using the linear theory. And we have boundary and initial conditions of your taste. And this is a beam of length L and thickness H. And we have material constants completely positive. And here, the W equation can be rewritten in this form. And you have this differential operator here applied to the second time derivative. And this brings extra difficulty in terms of controlling these beams. This difficulty is just because of the rotational inertia term that I'm circling out over there. So that term is simply discarded in engineering applications. So that takes you all the way to the so-called earlier Bernoulli beam model. So the only difference again is that you have no rotational inertia term here. And there's another model you may have heard of. It's called the Mindlin-Timoshenko beam model. So essentially you have a bunch of wave equations representing the longitudinal bending and the rotation of the beam, and these are all coupled, and you have the same type of positivity for the constants, as you can see. So now I want to talk about smart elastic beam model. So you have a piezoelectric beam model, which is essentially an elastic beam having electrodes at the top and the bottom. If you connect the electrodes to a circuit, you can start supplying voltage or charge or current to the electrodes, and depending on the amount and the type of the electrical charge, you can actually shrink or extend this beam. In fact, the opposite direction can also happen, so you can actually compress these materials or apply external force to generate electricity so that these materials are used as actuators and sensors. So after introducing the piezoelectric beam here, my research just starts here. In fact, now there's a lot of questions coming up. So how do we actuate these beams? Are we going to supply voltage, charge, or current, or even mechanical? Remember that when you apply force on the piezoelectric beam, we generate electricity. So what is the best actuation? So there are some answers for that. So traditionally, first off, piezoelectric beams are actuated by voltage. And why? Because it's easy to implement and you have simpler circuit design. And it's cheap, by the way. And it's a great advantage. And if you look at the pioneers in the field, including NASA, they all use piezoelectric beams actuated by voltage. And how about the choice of models? So should we go finite or infinite dimensional models? Can we use like circuit models, basic circuit models, RLC type? Are we supposed to use a linear or nonlinear models? How about the electrical hysteresis? So essentially, this is the electrical non-linearity that happens to a material. There's also mechanical hysteresis. Lots of hysteresis are observed, especially when you actuate these materials by voltage. And how about the nature of control operator? Because we're all doing control theory of PDs. So are we supposed to have like bounded or unbounded control operators in energy space, essentially? So this is also another question that we have to ask ourselves because in certain cases you have bounded, in other cases you have unbounded control operators. That depends on the choice of the electrical input. All right, on top of all of these questions here, there's another question that we should sort of like elaborate. We have to go to the basics. So how are you to model the electromagnetic effects? In fact, how do you model the interaction of the mechanical vibrations with the electromagnetic effects? Because piezoelectric materials are sort of like combining those effects. So then at the best, you can go with the Maxwell's equations for the electromagnetic portion of the modeling. But then you have three different assumptions over there: electrostatic, quasi-static, or fully dynamic. So I was reading the Yang's book, and he has a very good quote here. He just said that even though the electrostatic and quasi-static are more than sufficient to describe the vibrations on certain devices, in practice, there are some other devices, like, for example, piezoelectric acoustic devices that you can see in the diagram here, that you have the electromagnetic waves generated by the mechanical fields, and these are supposed to be accounted for. And if you use the electrostatic or quasi-static assumptions, you completely ignore those electromagnetic effects. Essentially, you have to sort of like incorporate these effects in your model by adopting the full set of Maxwell's equations. There is also another paper of Yang that was published in 2017 that he talks about the fact that at present there is only limited understanding of the electromagnetic effects generated by acoustic vibration, and because of the complexity of the electromagnetic effects being blended in mechanical vibrations. So even though for certain devices it's known that these effects are very major. People sort of like choose to discard, especially engineers choose to discard those effects because of the complexity that you add into the modeling process. So let's keep all of these things in mind, all of the questions and observation by Yang in mind, and now let's talk about the piezoelectric beam modeling. And here, for the mechanical effects, I'm going to use the Euler-Bernoulli small displacement assumptions, which is pretty common in the literature. We're going to assume that the edges are insulated, so no weird fringing effects. And we're going to have transverse polarization, essentially when you apply electric to the electrodes, and all the atoms are going to line up in the transverse direction, which is a pretty common assumption as well. We're going to apply charge or current to remove the hysteresis, because I mentioned 3 or 4 slides ago that if you use charge or current as your input, then the hysteresis, electrical hysteresis, reduce by 80%. So that's why I want to go with this type of setup here. And voltage is a totally different deal. I'll show you the model for the voltage, but it's a different deal. And we're going to use the linear constitutive equation, so we're going to have a linear model essentially. All right, here's the full set of Maxwell's equations coming along with boundary conditions. We're going to use either charge applied to the electrodes type boundary condition or current applied to the electrodes. And you can also apply voltage, as I said, but that causes a lot of hysteresis, and electric potential being equal to voltage is the boundary conditions corresponding to that, but I'm not going to consider this during the modeling process, but I'm going to show you the model if you assume the voltage boundary condition. And here is also the assumptions that I mentioned earlier. So are we going to use electrostatic, quasi-static, or dynamic? So let me just quickly explain what electrostatic means. So you have the magnetic field and the time derivative of the electrical displacement, body current or body charge completely discarded, and here the electrical field is the negative of the gradient of the electrical potential. And you can use quasi-static. Here the magnetic effects are not completely discarded because the time derivative of the charge is essentially not equal to 0. And even in this case, you can write E in this form, negative of the gradient of the potential minus the time derivative of the magnetic potential. And what we're going to do here is we're going to assume the fully dynamic model. That means I'm going to use full set of Maxwell's equations to start with. But I just wanted to show you the differences between all 3 assumptions here. So after adopting full set of Maxwell's equations, so we need to know how the stress and strain are sort of like related to electrical displacement and electrical field, and this is a well-known linear constitutive relationship. So these are all, by the way, matrices, submatrices, but essentially stress and strain has like 6 components, but we're gonna only assume that since we're using the beam theory. So we have the stress in the first direction, x direction, and then you have the stress in the z direction. And we also have the electrical displacement in x and z directions. So now we know how stress and strain are related to the electrical displacement and electrical field. All right, we have the final assumption before we wrap everything up. We're going to assume that the electrical potential and the magnetic potential are quadratic through thickness. Briefly, this is for involving the induced electrical field effects. So what we're going to do next is to write down the Lagrangians. We're going to write down the kinetic energy, potential, electrical, magnetic energy, together with the work done by the external forces. This is represented by the W here. So we only assume that there is just applied charge or current to the electrodes, and we have the surface continuity conditions, and we have the all pieces of the electrical and the magnetic fields to be our admissible displacements, and we also have V and W, longitudinal and bending motions. And if you sort of like wrap everything up and having better notation, we have a set of stretching equations. There's also another set for the bending equation, but since the current or charge control do not affect those, I don't mention them here. So one catch here is that the top equation is the wave equation describing the stretching of the beam, mechanical vibrations of the beam. And you have the second equation for the electrical potential. As you see that charge comes into the game together with the Dirac delta operator, so you have a boundary control. And if you assume the electrical current as your input, you can see that this is a nice Heaviside function. So it's a bounded controller popping for the very first component of the magnetic field component. Here we also have the boundary conditions: lateral force, first charge moment, and current. These are natural boundary conditions. And next, it's simply there's no way to use the current in the variation approach if there is no magnetic effect. So this is the importance of adding a full set of Maxwell's equations here. And bad news is that the system is not well posed. Essentially, the Lagrangian is invariant under certain transformations. You can find the details in those papers. And what is the remedy here? If you sort of like worked with Maxwell's equations and involving all the electromagnetic potentials, you have to rely on to a certain gauge. It's called gauge fixing to make the system well posed. But there is also the physics meaning of choosing a gauge. Essentially, if you use the Coulomb gauge, you assume that electromagnetic waves travel with infinite speed. And if you use the Lorentz gauge, electromagnetic waves travel with finite speed. So what is the reflection of that in the modeling or in the PDE here? If you use the Coulomb gauge, the circle term is going to be 0. So that's going to make the electrical potential equation not a wave equation, but just a elliptic equation that you can solve it for phi. And in fact, if you solve that for phi, let me just show you what you got here. So defining this psi operator, the inverse of this differential operator. So you sort of like eliminate the phi equation. So you have all wave equations here, and phi equations sort of like blended in through the other equations. So you have the charge, as you see popping up here with the Dirac delta operator as it was before, and you have the Heaviside function coming along with the current control. So this tells us that charge control is an infinite dimensional control, but or in other words, like unbounded type controller. Let's put it that way in energy space. And the current one is bounded because that's just popping as a nice Heaviside function in the right-hand side of the equation. The Coulomb gauge here is also blended into those equations, and it's an extra equation that you have to always keep in mind, especially when you design the energy space. And what happens if you use the Lorentz gauge? Well, then we're going to have a wave equation for the electrical potential as well. So there's going to be one more equation, and here is your Lorentz gauge added extra to the equation. So the deal is the same in terms of boundedness or unboundedness of the charge or current control operator. So you have the charge control unbounded and the current control bounded. And here is the model that we derive by using the voltage as an electrical input. So that requires another Lagrangian, another modeling assumptions. So I don't want to talk about that. If you just want to know more about it, here is the a reference to that, and please check back. But what happens here is that you have only the longitudinal vibrations, that's the V equation, together with the charge equation, that is in fact the P total accumulated charge on the electrodes of the beam. So you have different variables even in comparison to what you have for the current or charge actuation. So voltage comes into the play as a boundary controller. So I'll also give you some results on this model. This model is slightly easier to work with because you don't have any gauge fixing or nothing. You're just simply two coupled wave equations to deal with. All right, so far we only talked about a single piezo electric beam, and there are other models, obviously, 3-layer designs where you have piezoelectric beam is one of the layers, or even multi-layer designs, but because of the time limitation, I can't talk about those. But I'm going to put a link down the YouTube video so you can actually check those models if you're interested. All right, let's change the gear a little bit. I'm going to talk about the controllability results for the Coulomb gauge and Lorentz gauge models, and I'm going to also talk about the quasi-static and electrostatic cases. And here we go. We have the energy involving all the electromagnetic effects and the mechanical effects. We define this Hilbert space. One problem with the Coulomb gauge is that you have to sort of like involve that Coulomb gauge in the game, especially in defining the energy space. So you have the inner product, and this inner product on the linear space H defines a norm. And H is a complete space. That's important. States are going to follow the energy description here. So we're going to define those states, 5 states, and here, as you see that the current control comes into the play like this. By the way, I'm just talking about the current control at this moment, and when I write down the state space formulation. And we have this matrix A, and we have the domain that also involves all the boundary conditions and a Coulomb gauge, and you define the control operator and the observation operator, which is B star. B star is going to be our measurement. All right, here are some technical results. If you're interested, you can check the paper. And the most important part here is that with the choice of H, we can show that A star is exactly equal to negative A. We have a unitary semigroup, and we have the well-posedness result in H. Right now we're looking at the time derivative of the energy, and we can observe that this is current times the integral term over there. That integral term corresponds to B star feedback, and what we do is just we feed it back into the state space formulation, and that B star is very physical. In fact, that's the magnetic current in X direction. So we have a dissipative system, and the closed loop system is in fact well posed, and we have all isolated eigenvalues. All right, now we have a well-posed system. It's time for proving the lack of stabilizability. And for real tau, we define all of these constants ABC written in terms of the material parameters, and we have A1 and A2 written in terms of ABC. So we have a very technical result, and if you're interested, please refer back to those papers here. So you have, if A1 and A2 are of special forms, 2n pi over L, 2n pi over L, m and n are integers, and m squared plus n squared is strictly greater than that constant here, then we have the lack of asymptotic stability. In fact, in the engineering literature, it's the minimum you ask for when you talk about stabilizability. And we, in fact, went further and proved that the system AB, with B being the control operator, is not asymptotically stabilizable, not just by B star feedback, but by any other bounded state feedback. And it's just because that, first off, the current control produces a bounded control operator, and there's no way to push all the eigenvalues to the left half plane, which is pretty much expected. And we use the Benjamin's theorem to prove it. And how about the charge actuation? I didn't want to go through the details of that in terms of the state space formulation, but if you use the B star measurement, in other words, that's totally mechanical. So you're talking about piezoelectric beam, so you should normally control an electromagnetic quantity and measure the same way, but if you go with charge, you in fact have to measure something mechanical, which is a tip velocity, and show that you have the same type of lack of stabilizability result. And how about the Lorentz gauge? Lorentz gauge, I would just say that the setup is pretty hard. And again, if you're involved in Maxwell's equations with the potentials, proving well-posedness for a Lorentz gauge is a big deal. I worked on this problem for a long time, but eventually I got it published, and it's well-posed. But you have to redefine your state, and you have to sort of like convert the Lorentz gauge into a Coulomb-like gauge, and you define the inner product and the space accordingly. And I'm going to skip those details here, but just show you that B star is also calculated through that. We have the well-posedness result with the new set. In fact, we had to embed the new Coulomb-type gauge by converting the Lorentz gauge into in our Sobolev space. And again, that was quite technical, so please refer back to my paper here. And similar to Coulomb gauge model, you can define ABC, and you can prove a very similar result of the lack of asymptotic stability. And in fact, there's no way you can stabilize this model by any state feedback. Okay. How about the electrostatic or quasi-static cases? In fact, that's pretty interesting, because if you don't assume the full set of Maxwell's equations, life is so easy, because you have a single wave equation, as you see here, and it's controlled by the charge controller, or you can use the circuit equation, as you see that the time derivative of the charge is the current, so you can actually use those separately. And you can easily prove that both models are at least asymptotically stable, but obviously the model controlled by only charge is exponentially stable. And you can refer back to this result of Vehbe for the polynomial stability in the case of current. Remember, in the fully dynamic case, we don't have the stabilizability, but here we have at least some sort of like a stability, which is good in terms of practical purposes. And this table sort of like summarizes everything that we have so far. You can go with electrostatic, quasi-static, or dynamic assumptions of the Maxwell's equations. And if you go with the voltage control, you measure the induced charge and it's not asymptotically stable. But if you go with, again, electrostatic or quasi-static, everything is good. You even have exponential stability. And in the charge control, it's the same deal. With the dynamic approaches, you don't have asymptotic stability. But anyway, so this lists all the weirdness coming along with choosing different assumptions in the modeling process. And in terms of the control, you have like all different types of controllability or stabilizability results. All right, let's change the gear a little bit. So in this part of the talk, I'm going to mention related results involving certain other physics into those PDs. And all of these models, by the way, are novel, and that's why we wanted to analyze these models with delay, memory, thermal effects, and fractional damping. And all the slides that I'm going to show you are not going to contain any mathematical results because these are all submitted work, but at least it may give you some idea about like what problems I have been working on so far. So you may add different types of delays, like for example, distributed delays, or delays in the mechanical boundary condition or the charge boundary condition, and you can analyze what is at stake in terms of stabilizability. And time delay is sort of like important because a little delay or small perturbation delay in the output measurement causes instability. So here we submitted multiple papers involving those delays, different types of delays. And we got really nice exponential stability results following certain papers, following certain results in the literature, and we utilize a Lyapunov approach for this type of model specifically. And this is, remember, this is a model corresponding to the voltage control case, and for current charge control, this type of delay was never ever studied. And next is how about like adding memories to each equation. So you have the mechanical memory, and this is in fact an interesting behavior. So we know the elastic memory, but really we don't know much about creep or dielectric relaxation, and you can't find really models in the literature taking care of that in the infinite dimensional setting. So this part of the model is very important. Again, this was never ever studied before with this much of rigor blended into the PDs. So this is another problem that we worked out. And in fact, there's different versions of that, but we added some external forces and source terms and some kind of like a damping, magnetic damping into one of those equations. And we proved under certain conditions that we proved the dynamical system associated with the solutions of the system allows us using the quasi-stability theory so that we get the existence of global and exponential attractors. And again, this model has never been considered in the literature due to the existing complexity of the PD models for piezoelectric beams. So this is the first stab of adding the memory term in the piezoelectric beam equations. And what if we have the fractional damping and thermal effects? So this is also not studied at all. So we got essentially the piezoelectric beam model actuated by the voltage. So we add the frictional damping, magnetic damping into the P equation, and we added the thermal effects that's coupled to the piezoelectric beam equations, and we proved a lot of stuff here. This is a long paper, by the way. So we studied the long time dynamics, and we just proved that the dynamical system generated by the system has a smooth global attractor with finite fractal dimension by the quasi-stability theory. We got the existence of the exponential attractor and a global attractor on the perturbation of the fractional exponent. So this is also a joint work. We submitted this work. It's under revision, so I can't really share the details, but I can briefly explain. I briefly explained what is accomplished in the paper. All right, in this part of the talk, I'm going to mention non-linear models. I'm going to only consider the voltage control just to show what's going on here. And before I start, I want to point out that the nonlinear effects are crucial in modeling because they explain certain behaviors, especially for energy harvesting purposes. So these accounts should be accounted for. And when I started modeling this, I wanted to use both large displacement assumptions due to Mill and Timoshenko and Euler Bernoulli. And for the electromagnetic effects, I'm going to involve everything due to Maxwell's equations. And if one wants to get down to quasi-static or electrostatic model, and there's a way to eliminate certain variables to get down to PD models for those cases. When I first looked at the results or modeling papers spitting out distributed parameter models, I can highlight the work of Kugi and Schlascher, and they interestingly got the bilinear control system, which is very similar to what I got here, but they obviously assumed electrostatic assumptions. They got hinge boundary conditions, and the longitudinal inertia term is sort of like ignored. That's pretty interesting because in involving nonlinearity, one observation is that the longitudinal motion is strongly coupled to the bending motion. So if you sort of like discard the longitudinal inertia and design the controllers, it's a big reduction, I would say, the least. And there was another paper by Wallace and Sherpin. They used clamp boundary conditions, and they showed that with only one controller, quasi-static model is not stabilizable. With two controllers, fully dynamic model is stabilizable. This is a good result because this is the most rigorous paper I have seen so far involving nonlinearity. And unfortunately, there are no other distributed parameter modeling and control results for cantilevered boundary conditions involving all electrostatic, quasi-static, fully dynamic models. First off, again, because of the time limitation, I can't show you everything. I will only show you the electrostatic case here, just to show you what's going on. And you can see that V equation is strongly coupled to the W equation. And you have this non-linear term popping here, and that's sort of like popping in both equations, and that's somehow like how these equations are blended. But more importantly, different from the nonlinear elastic beam models, there's the voltage control popping in two different parts of the equations, and the first one is sort of like a boundary control, and then the other one is the distributed control. So that's what I'm saying. So if you just use the elastic beam modeling to incorporate nonlinearity, you won't get much, because if you look at those models, this term doesn't exist. This term sort of like doesn't exist. That's why you have to use the fully dynamic approach first, and then reduce everything down to electrostatic to see the full effects of the voltage controller. And again, this is a very novel model. You probably haven't seen this model anywhere. Please check this out if you're interested. And what we did here is that we also added some controllers, moment and shear, transverse shear controllers for the bending equation. All right. So how do you stabilize even the electrostatic case? Well, we look at the B-star type feedback, and that B-star type feedback is interesting here. So you have the tip velocity, and you have the time derivative of the integral of Wx squared. That's an important term. That's the effect of nonlinearity, so like coupling the V and W equations. And we choose like classical B-star feedback controllers. You have a dissipative system, but essentially this part is important because the tip velocity could be the negative of this component, so that could zero all the effect of the feedback for the voltage. So you're gonna sort of like eliminate that case. Okay, so that means like there are some other non-trivial equilibrium points going on here, and the analytic work is underway with collaborators, and I can't show you the results here because of the same reason. So if you free the mechanical controllers and discard all the nonlinear effects, so you have a perfectly decoupled equation, as you see that the voltage only controls the longitudinal motion but not the bending motion. So again, nonlinearity is important because voltage affects both stretching, longitudinal motion, and the bending motion altogether. And if you consider the earlier Rayleigh D model, not the Minden-Timoshenko, you can put it in the space-space formulation. By the way, you can choose the classical states to start with, but there's also different choices of states. Like for example, I can change this to v sub x 1/2 wx squared. So I get a different state space formulation, and I can prove different results for that. But we prove that this system here is a nice boundary control system. One of the catches here is that the voltage control pops here in a bilinear way. This was the observation in Kugi, and we got the same observation here. Again, there's not much work done for this type of systems, and if you're interested, this could be like an interesting mathematical problem. We already start working on it, and we got some preliminary results, but I can't share those with you at this moment. But there is a lot of open problem here. So we proved the well-posedness, exponential stability is sort of like proved. It's a preprint right now. Different combos of boundary feedback and distributed damping are in consideration right now. So if you're interested, please, like we can do some joint work in the near future. And we got the numerical work, which I'm going to show you in little details here, but there's supposed to be lots done in the near future. So again, if you're interested, please contact me. So here's some numerical stuff going on here. If you have uncontrolled early Bernoulli beam, as you see that it's a mess. So there's no control going on here. So V and W are just fluctuating all the way. And if you have a fully controlled model, essentially you have V, M, and G, all three controllers. So as you see that both stretching and bending motions are controlled perfectly here. And if you have partial control, for example, voltage is non-zero, but all other bending and transverse shear, moment and transverse shear controllers are zero. So we have only voltage essentially. So voltage handles the stretching pretty well as expected, but it doesn't control the bending motion at all. And if you have M and G, so you control essentially the bending equation, but not the stretching equation, because we have V voltage to be zero. So stretching is not controlled at all, but bending is controlled. So you need two controllers at least to make the system stabilizable, because voltage apparently is not enough. And you have the tip velocities here, so no control, you have a lot of fluctuations going on. Controlled tip velocity, you have a very good result here, so that V n dot is essentially tip velocity is just decaying to zero pretty fast, and if you have the partial controlled type 1, so you have essentially bending equation controllers only, so you can't control V dot as you see the tip velocities. But if you have only voltage controller, tip velocity is good, but this time you can't control the bending motion. So you need two controllers at least. That's the sort of catch of that. And same thing with the W dot equations, essentially. And if you look at the normalized energies, the best case here is the both controlled case. The decay is almost like exponential, as you see. But if you look at no control or partially controlled number 1 case, these are not good cases at all. There's some sort of like decay, but not exponential, obviously. And voltage control is very strong because it has the effect on stretching and bending, essentially. And you pretty much observe the same type of pattern in the Minden-Timoshenko case. All right, let's change the gear a little bit again, and this time I'm going to talk about the numerics for infinite dimensional systems. And working on the numerics for infinite dimensional systems is important because most of the time the control design is infinite dimensional, but in practice we have to reduce those down to a finite dimensional model, so the control design is finite dimensional. So we're going to be very careful with that. And the toy problem that I picked here is the Rayleigh beam equation, and this is a published work, but there is more work coming along with that. But the reason why I present the Rayleigh beam equation is just because it's easy to present. All right, let's move on with that. Observability. So here we go. We have the Rayleigh beam equation, and we choose the hinged boundary conditions to make our lives easier. This boundary is controlled by a controller U of t. So essentially, we're controlling the moments at the tip of the beam, and we have all the material constants positive. So what I'm going to do next is to rewrite this term. Then we have this operator so that we can convert this differential equation into the first order form. And now we choose the states to be W and the time derivative of W so that we have this system operator. As you see that we are supposed to invert this matrix. Now we're going to define the solutions in the higher order energy space. We're going to define the inner product and in fact inner product induced norm. And then we have the following result. We prove that if T is greater than twice of the length divided by the speed of wave propagation on the beam, then we prove observability, which essentially means that if you measure the third derivative at the tip of the beam for enough amount of time, so the t must be greater than this number, then we have this observability inequality holding true. So essentially what this means is that the PDE model is exactly observable. Now I want to go back to the differential equation model here. So this is a partial differential equation, and this is an infinite dimensional model. And if you were an engineer and if you would like to design a controller or an observer, you would have to discretize this model so that you would reduce this infinite dimensional model to a finite dimensional model. So interestingly, if you apply the known approximation techniques, so many things failed substantially. And I'll show you one of the results that they use so many known techniques, and those known techniques fail to mimic the observability properties of the PDE. So in fact, this is the paper by Banks and Wang, and please refer to that. And they were considering a simple one-dimensional wave equation describing vibrations on a string, which is clamped on the left end and free on the other end, but free end is controlled by this controller here, which is in fact measuring the tip velocity and then feeding it back to the right end boundary condition to make all the solutions to be exponentially stable. And it's proven, it's a known fact that these solutions are exponentially stable, and then all the eigenvalues are sort of like shifted to the left half plane. The first technique they practiced was the polynomial-based Galerkin approach, and if you increase n from 3 to 9, you still have eigenvalues getting a little bit closer to the imaginary axis. I would assume that there is some kind of like a uniform gap between the maximum of the real parts of the eigenvalues and the imaginary axis. The next numerical technique they practiced is the linear spline-based Galerkin approach. As you see that when n equals 10, there is no uniform gap between the imaginary axis and the maximum of the real parts of the eigenvalues. So they also tried the cubic spline-based Galerkin approach. The situation is the same. Failure is substantial. And in the fourth approach, they used the finite element, so-called finite element approach, which is pretty widely used approximation technique. The situation is even worse. And remember, in the PDE setting, we have a uniform gap between the eigenvalues, real part of the eigenvalues, and the imaginary axis, and that's why we get the exponential stability with the fixed decay rate. And here is the finite difference approach, which is another easy technique to apply. As you see that this situation here is even worse. So eigenvalues get extremely closer to the imaginary axis. And finally, let's see, we have the mixed finite element approach. I think this is the best of all the techniques they applied. In fact, they mentioned in the paper, so that you have some kind of like a gap happening here, right? Some kind of gap happening here. At the time of the publication of this paper, the authors, in fact, didn't realize what the problem is, because these are known techniques. And what was the problem? And the problem was simply because of the eigenvalues of the control-free problem in the PDE setting. Those eigenvalues have a uniform gap, which is a well-known fact because you're talking about the wave equation. But when you look at the reduced models and their eigenvalues, you realize that the eigenvalues flatten out when you go to high frequency eigenvalues. So that means for the high frequency eigenvalues, the uniform gap is lost. In fact, the gap approaches zero as the MASH parameter goes to zero. So that was a problem. Now I would like to quickly talk about the remedies proposed in the literature, and the first one is called the filtering technique, and that has two different ways. And in the direct filtering technique, you just cut off the high frequency eigenvalues starting from a threshold number that you pick, and then you discard the high frequency ones and you continue with the leftover eigenvalues and eigenvectors. And if you want to work with higher frequency eigenvectors just because you're interested, you can let the mesh parameter go to zero. You can have more eigenvalues in the list, and then you cut off from the higher numbers. So that's what the direct Fourier filtering is about. And I'm going to also talk about that and the results that I'm going to use today. And in the indirect filtering, you essentially add a viscosity term to the PDE with a mesh parameter in front. And when you let the mesh parameter goes to zero, so essentially viscosity term helps stabilize the solutions and in fact mimic the solutions of the PDE problem. And then as h goes to zero, essentially that term disappears and you have a good convergence result happening. You also have mixed finite element, which is pretty good in fact, and there are some researchers worked on that. There's a two-grid algorithm, and there's also a paper just came out that uses the finite difference method without filtering, without viscosity term or without Fourier filtering. And that's an interesting paper. You can check that out. And the rest of the talk, I'm going to choose this technique applied to the beam equation, and we also get a uniform observability as the mesh parameter goes to zero. Now we're going to use the semi-discrete finite difference approximations, and for that reason we're going to split the interval 0L into sub-intervals, and we're going to call the endpoints to be the nodes x0 through xn plus 1. And at each node we're going to approximate the solutions by using the W sub I type notation here. And just because we have a fourth order differential equation, we need to define fictitious points here. One is xn plus 2 and the other one is x sub minus 1, because we have two second order boundary conditions and they have to be defined. So for that reason we define these points to be asymmetric. So this is sort of like the necessity for hinged boundary conditions. So now we are approximating the second and the fourth derivatives by using the central differences, so that we have a system of differential equations with homogeneous boundary conditions on the left and right end, together with the asymmetric boundary conditions. What we want to do is to come up with the eigenvalues of this system, but to achieve that first we need to solve an auxiliary eigenvalue problem, which is in fact, you know, this negative second derivative operator approximated by the central differences. So we first solve this eigenvalue problem. In fact, if you want to write that in the matrix form, and you are looking at the eigenvalues of tri-diagonal symmetric matrix. And this matrix is a positive definite matrix, so you can list the eigenvalues from lambda 1 through lambda n. It turns out that we can list the eigenvalues and eigenfunctions of AH explicitly, analytically. So eigenvalues follow this form and eigenfunctions follow sign type form, which is pretty much expected because the original problem, the PDE problem, has sign type eigenfunctions. So now we're letting this vector to be our state. W1 through Wn, and we convert the discretized Rayleigh beam equation to this form. And next, we're going to try coming up with eigenvalues of this boxed matrix here. So in fact, that matrix is positive definite, and we know that all the eigenvalues are positive. And here are the eigenvalues and eigenvectors of that matrix. So in fact, we have k over alpha that has something to do with propagation speed. And this is lambda kh, the eigenvalues of the matrix AH. And we have the tail coming along. We have the eigenvectors following the same form as in the case of AH, like this one. Okay. And we can normalize the eigenvectors with the normalization constant. And it's in fact easy to prove that lambda kh, which are the eigenvalues of AH, times h squared is less than 4. And we can also prove that lambda k twiddle h squared is less than 4 times k over alpha for all h positive. Also, if you consider the last eigenvalue of this matrix here, so that eigenvalue times h squared converges to 4k over alpha as h goes to 0. Now let's get to the bottom of the problem that was first observed in 1990. I mentioned that in the beginning of the talk. So we're plotting the radical of the modula of the lambda twiddles for k and alpha to be 1. So the wave propagation speed is going to be 1. So we have the eigenvalues of the PD problem. In fact, they're infinitely many, but they follow a linear pattern. And we also plot the discrete eigenvalues for different choices of the number of nodes. And you can see that after certain point, the eigenvalues flatten out. So what that means is we're diverging away from the original eigenvalues of the problem. So convergence is an issue here. But the question is like, is that the only issue? No, that's not the only issue, because if you look at the uniform gap between two consecutive eigenvalues, you can observe that the gap converges 0 as you increase n, and if you are considering the high frequency eigenvalues. So when the uniform gap is lost, you can't talk about the observability inequality. In fact, you can show that as h goes to 0, the gap goes to 0. For that reason, not only we lose the convergency, but the uniform gap condition that the Rayleigh beam equation has. In fact, you can pick a solution of the discrete problem, and you can just show that for that type of solution, you lose observability. Essentially, observability constant tends to infinity as h goes to 0, whereas we proved in 2011 that the original problem is exactly observable with this optimal control time. This result shows that we proved the lack of observability of the discrete model because we simply applied the finite differences blindly, and whereas the original problem is exactly observable. Now let's filter the high frequency eigenvalues and eigenvectors, because these were the ones causing the lack of observability. So here is gamma, our filtering parameter. It's in between 0 and 4, and we consider filtered solution. So essentially you fix gamma to a value in between 0 and 4. Essentially whatever gamma is, you're going to keep certain number of eigenvalues. And for those solutions, you can easily prove that the finite dimensional system is exactly observable with this observability constant. Here, notice that the observability constant depends on the filtering parameter, and in fact, the observability time also depends on the filtering parameter. So we can actually have some experiments here. So we can choose gamma to be 3 for n equals 50. So that means we're going to retain only 33 eigenvalues. And if you are choosing n to be 100 and gamma still to be 3, so the cutoff is done at 66. So we, in fact, keep the first 65 eigenvectors. So if you want to keep high frequency eigenvectors in your solution, so that means you need to increase n, and you need to choose gamma in between 0 and 4 to retain those high frequency eigenvalues and eigenvectors. All right, here is the Wolfram's demonstration project, which is already available at Wolfram's website. So this one is specifically for Rayleigh beam and Euler-Bernoulli beam, and for your reference, we have another one for the wave equation and the boundary damping with that. We also use the filtering technique for that. And this demonstration project is more about the design of the feedback controller by using the observation. So it's very connected to what we have been doing so far. But we're using a different type of filtering. In fact, we added a viscous damping type filtering to the equation to suppress the vibration. So just so you know, this is sort of like a representative example. And we also have a demonstration project where we have the direct filtering, but I think this one is already available, so I wanted to present this one. So here we have the Rayleigh beam or Euler-Bernoulli beam. You can just sort of like pre-select that. And we have the filtering either 0 or 1. And we have n to be the number of nodes in the discretization. As you see that we have 20. We already have filtering 1, so we're talking about the filtered solutions in the next simulation. And we have the viscous damping, and we have no boundary damping for the time being. And we have the normal mode displacement. We got the 15th eigenfrequency mode as the starting point, as the initial condition, without the initial velocity. So let me just start the demonstration. With the viscous damping, we have a really fast decay. Now we are going to choose another version of this. So we have the filtering, and this time we have the boundary damping. We have a pretty fast decay as well. And the next is that we remove the filtering. All right, we remove the filtering. We still have the boundary damping just for you to see the difference between filtering and non-filtering. So essentially the solutions are not really decaying to 0. 20, n equals 20, and I got the 20th node, very last eigenfrequency mode as the initial condition. Let's see what's going on here. So as you see that we have the filtering on right now, and we have the exponential decay of the solutions, even for the highest frequency solution. All right, so as I said, feel free to download these demonstration projects from the Wolfram's website. As long as you cite our work in your research, if you ever use them, we really appreciate, because there's a lot of effort coming from my students supported by NSF grants. So we totally appreciate if you recognize this work. All right, this is the end of the talk. Thanks much for your attention, and I'm ready to pick up the questions. But beforehand, if you're not watching this video live, and you're probably watching this in the organizer's YouTube channel, please put your questions and comments down there. I'll try to address your questions. Thank you so much.